Good morning to all. Today we can discuss about the Clapp oscillator, which is a type of LC oscillator in the subject analog electronics. So Clapp oscillator. So what is a Clapp oscillator? The Clapp oscillator is similar to Colpitts oscillator except it contains one additional capacitor C3 connected in series with the inductor L in the tank circuit. So what is the tank circuit? So this will be the tank circuit C1, C2, L and C3. So in Colpitts oscillator, you don't have that C3. So now Clapp oscillator is formed along with the inductor L, a series capacitor C3, which forms which is used for mainly frequency stability. So that is the major advantage of using one more series capacitor along with the inductor. So in the Clapp oscillator, Z1 and Z2 are the capacitors C1, C2 and Z3 is the series combination of inductor L and capacitor C3. So addition of the C3 improves only the frequency stability. So the resistors R1, R2 and RE in the circuit R1, R2 and RE. So these R1 and R2 which is the voltage divided biasing resistors and R along with the RE is used for DC bias. So that is what I explained here. So provide the necessary DC bias to the transistor. C is the bypass capacitor, CC1 and CC2 are the coupling capacitors. So that you know already. So working, how it is going to work when the supply voltage is switched on. So whenever you are going to increase your DC voltage, what happens is a transient current is produced in the tank circuit and which will be leading to some oscillations in the circuit. So this oscillatory current in the tank circuit produces an AC voltage across C1 and C2. So terminal 3 is it will be at zero potential. So if terminal 1 is at a positive potential with respect to 3 at any instant, terminal 2 will be at negative potential with respect to 3 at the same instant. So what happens is between 1 and 2 terminal, there is always 180-degree phase shift. So here 1 and 3 in the circuit, you have 180-degree phase shift and the second shift between that is 3 and so totally what is the phase shift you have achieved is 360-degree. So this is the necessity condition for oscillation. You need to have 360-degree oscillation, but how it happens in Clapp oscillator is between 1 and 2 and 2 and 3 since it is grounded. So how to derive the condition for oscillation and the frequency of oscillation of a Clapp oscillator. So how we will be starting for all the types of oscillators? You have already we have derived the general equation for LC oscillator. From there we have to start. So HIE into Z1 plus Z2 plus Z3 plus Z1 into Z2 into 1 plus HFE plus Z1 Z3 equal to 0. So since Z1 Z2 are the capacitors and Z3 is the series combination of an inductor and a capacitor. So the product terms Z1 and Z2, Z1 and 3, these terms forms the real part and Z1 plus Z2 plus Z3 into HIE forms the imaginary part. So in order to achieve the condition for frequency of oscillation, imaginary part should be equated to 0. So HIE into Z1 plus Z2 plus Z3 is made to equal to 0 means Z1 plus Z2 plus Z3 is equal to 0 because HIE cannot be made to 0. So Z1 is equal to 1 by j omega C1 as we have defined it is the capacitor and Z2 equal to 1 by j omega C2. Z3 is the series combination. We are going to substitute this Z1 value, Z2 value and Z3 value in this equation. So when substituted, you will be getting the value and simplification, you will be getting omega square equal to 1 by L into C equivalent. So what is that C equivalent? It is nothing but 1 by C1 plus 1 by C2 plus 1 by C3. Since the capacitors are the capacitors, the equivalent circuit will be formed by the series connection means it will be nothing but 1 by C1 plus 1 by C2 plus 1 by C3. So that is nothing but taken as 1 by C equivalent. So you will be getting what is that F omega since omega equal to 2 pi F, it is 1 by 2 pi root of L into C equivalent. So that is nothing but the frequency of oscillation. Next thing is you have to obtain the condition for oscillation. To find the condition for oscillation, you have to put the real part to be 0. So the real part is in the general solution, the second part. So when you are putting, when you are equating that, so Z1, Z2, we are bringing that Z1, Z3 to the next side. And after simplification, you will be getting 1 plus HFE equal to Z3 by Z2 minus Z3 by Z2. What is your aim to find the condition for oscillation? Means now you have to obtain the value of HFE. So now you know the value of Z3 and Z2. Z3 is j omega L plus, plus 1 by j omega C3. And what is the value of Z2? It is 1 by j omega C2. So you are going to substitute that term and simplify. After simplification, you will be getting omega square LC2 minus C2 by C3. Already we have derived that the frequency of oscillation F equal to 1 by 2 pi root LC equivalent. So from that, you can take that omega square L value and substitute over here. So when you are going to substitute that, and after simplification, you will be getting that HFE is equal to C2 by C1. That is the ratio between the capacitor C2 by C1. It does not rely on C3 because frequency of stability means we need to have stability means the only thing it is going to affect is the frequency of oscillation. It does not depend on the condition for oscillation. Since it is involved only along with the inductor L, it does not affect anything in the condition for oscillation. Only thing is there will be change in the frequency of oscillation in the C equivalent value in compared to the Colpitz's oscillator. So that is about the Clapp oscillator.